Okay, um, in this last video, I want to talk about something I like to call higher dimensional sample spaces. Okay, so when we roll one dice, we can think of that as, the outcomes are the numbers 1 through 6, right? And you could list them out in a row, kind of like on a number line. 1, 2, 3, 4, 5, 6, and that is like a one-dimensional sample space. Right? Now, if you rolled 2 dice or you did 2 things, right? Then you have a square. So like this is the first dice, this is the second dice, and then your sample space is now a 2-dimensional sample space, right? And there's 36 outcomes. So this idea of sample space, that's a good name because these are spaces in a sense. You have the rolling 1 dice is a 1-dimensional space. Rolling 2 dice is a 2-dimensional space. So now if I rolled 3 dice here, right, and I wanted to list out the sample space, do you see what you would have to do here if you rolled 3 dice? Is you would have to have an axis. You would need to have an axis here coming out of the paper and rising up, having the numbers 1 through 6. And that would create a cube of numbers, okay? And the number of numbers inside this cube would be 6 by 6 by 6, kind of like taking the area of a cube would be length times height, or length times width times height, right? And so 6 times 6 times 6 is, I think it's 234. Let me make sure. Oops, 216. So there would be 216 outcomes if you rolled 3 dice. Okay? You would have 216 outcomes, and now your sample space would be 3-dimensional, right? You would have another axis coming out, and you would have a cube of numbers, okay, where the 1, and then up 1 in that corner, this bottom corner over here, you would have 3, that would be the smallest, and then 6 by 6, and then up 6 up in this corner, so you'd have one, the lowest here, the greatest up here, and this would be like 18. 6 and 6 and 6 is 18. And then you'd have all the numbers in that space. Okay? Now notice if I rolled a 4th dice, guess what happens here? Okay? Well, you could get the outcomes, the number of outcomes really easy. You'd have 6 times 6 times 6 times 6, right? You'd have that 216 times 6 more. You'd have like 1,296 outcomes. Okay, but now the sample space, how could you lay out the sample space, right? You already have the 3rd dimension being the 3rd dice. Where would you put the 4th dimension? Well, you only have 3 dimensions. Our space only contains these 3 dimensions. So you would have a 4-dimensional sample space, and you couldn't even picture it. It would be very, very unusual. Okay. And if you added a 5th dice, like you do with Yahtzee, you could easily get all of the outcomes, but now you would have a 5-dimensional sample space, which would be even more complicated than a 4-dimensional sample space, right? So you have these higher dimensions, and you got the outcomes actually existing in a higher dimensional space. So if you've ever wondered, why do these mathematicians think about things outside of 3 dimensions? Well, it's not because they're like Einstein and they're weird or they're thinking of relativity. It could be they just want to know what the probabilities are for a game like Yahtzee, right? Something that simple. Anytime your outcomes exceed 3 actions, right, your sample space has a higher dimension to it, and the math becomes a lot more complicated. So you can see why probability is a very interesting branch of mathematics and why it can get very complicated. And you don't have to know any of this. This is just for you to kind of see and understand how the higher dimensions plays a role in mathematics. Okay, but let me show you one more thing, and this comes from something I put together for a STEM fair one time, and that is kind of trying to help you understand what the fourth dimension might be like a little bit. And the way you do it, remember, math is the science of patterns. So as you go from 1 dimension to 2 dimensions to 3 dimensions, then you can take the patterns that occur as you increase from 1 dimension to the next, and then you can take those patterns and carry them another dimension further, and then you can actually say some meaningful things about the fourth dimension. And so let me show you something that I've put together here, and this is for STEM fair. So 0 dimensions here is just a point. Okay, very uninteresting. A point is 0 dimensions. So 1 dimension is where you take that point here and you actually move the point along in one direction. A dimension is kind of a direction. 1 dimension, 1 direction, and then you got this other point over here and you got the line between them connecting the 2 points. And you've created a 1-dimensional space, and a 1-dimensional space is just a line. So what would a 2-dimensional space be? Well, what I did here is I took the 1-dimensional space and I moved the 1-dimensional space, and I connected them together to get the, I took the 0-dimensional space, I moved the 0-dimensional space, and when I connected them together, that created a 1-dimensional space. Well, now this is my 1-dimensional space, this line, and I'm going to move that line in another direction. So this is the 2nd dimension, this direction. I'm moving the 1-dimensional space from here down to there, and I'm connecting these 2 sides. And when I do that, I get this 2-dimensional space. And that 2-dimensional space here is a square. And so now to create a 3-dimensional space, what I have to do is I have to take that square, that 2-dimensional space, which is back here, and I would have to move it off of the paper or off of the screen out in a 3rd direction, okay? And that's what gives it 3 dimensions. So this square gets moved in this direction, and then you connect the 2 spaces there and you create this 3-dimensional space, okay? So what about a 4-dimensional space? Well, this is actually a 4-dimensional hypercube, and it gets really confusing here. But look at this. See this 3-dimensional space? Here it is. You can kind of see it right there. It's shaded. It's that cube. And what I'm going to do is I'm going to move the cube into a 4th dimension. And the only problem here is I can't picture what it would be like moving it into the 4th dimension because we only have 3 dimensions. And here I'm trying to do it on a 2-dimensional surface, right? But I would be moving it down to here, so up there, down to there, and I'd be connecting all those corners, and that would give me this 4-dimensional space. And what it ends up happening here is like this line here. When you make the 2-dimensional space, I now have 4 lines, okay? And then when I move that square into the 3rd dimension, I now have 6 squares, okay? And so when I move this into this dimension, you actually get 8 cubes. There's 8 cubes. So this hypercube has 8 faces, and the faces are not a 2-dimensional surface like this. The faces are a 3-dimensional cube on each face. It's kind of weird, but that's what it is, okay? And so that's kind of, you're taking these patterns that occur here and you're extending them to say meaningful things about the 4th dimension, okay? So now here's actually a glimpse inside the 4th dimension. I found this is a rotation here. And this kind of is neat looking, but this one's actually, I think, a little more insightful, even though it's a lot simpler here. And the reason I think this is insightful, as it spins around, you can see there's just a second where it looks like a cube, exactly like a cube. And that would be kind of analogous to if I were spinning a cube around and it got faced towards you in exactly the right way, so that all you saw was the face of the cube, and so it would look like a perfect square for just a second, and then I keep rotating it and it would be that cube. Well, similar here, there's just a second where it looks like a perfect cube. Instead of a cube looking like a perfect square, this is a hypercube looking like a perfect cube. And you're seeing the face, one of the faces, one of the 8 faces of the hypercube. So it's very, very interesting. So let me go back here and let me just share. Yeah, my son here. Zachariah, let me finish this video, okay? So let me just share one other thing here. You could then take this and you could extend this to, what if I ate at 3 different restaurants? We randomly selected 3 restaurants. What would be the probability we could afford all 3 restaurants? Well, what I could do here is I could move this up like this, okay? And then I would have a cube with all these different prices, and all the prices would be the prices of the 3 different restaurants. And the only one that we could afford with a $60 budget is the cheapest one, 18 plus 18 plus 18. We could afford that. That would be $54, so we could afford that. But if we even ate once at the second most expensive restaurant, which is $25, you see that it's then $61. 18 plus 18 plus 25, can't afford it anymore. So the only restaurant we could eat at would be the one down here, where we would have 18, 18, up 1 would be 18, and we could afford that one. All these other ones would be too expensive. So it'd be like 1 over, and it would be 5 times 5 times 5, and that's like 125. So the probability we could eat at all the restaurants would be like 1 out of 125. So you could see how you could take these other examples and extend it to further dimensions. Now, if I were to ask, like if my budget was $100 and I were to ask how many restaurants you could eat at, it would be a lot harder to tell. There would be numbers in our cube that would be less than $100, some that would be more than $100. You would have to almost make a cube in order to figure it out. One way you could do it is you could take the 5 cross sections, and this could be, you could have one cross section where you're adding $18 to all these. The next cross section you're adding $25, and then you're adding 28, and then 37, then 52. And so you'd have 5 spaces like that. And then you could actually count all the ones that would be less than $100. So you can see how the math gets a lot more complicated, a lot more interesting, how you would need higher techniques in order to solve them. Please do not worry about any of this. I'm just trying to give you a glimpse into some of the things that occur with probability, and also why mathematicians even bother thinking about higher dimensions, because they come into play when you're doing real life problems.